The first law of thermodynamics states that the total energy of the universe, or an isolated system, cannot be created nor destroyed. Rather, it can only be transformed from one form to another. It implies that the total energy of an isolated system is always conserved. This chapter examines the ways in which a system can exchange energy with its surroundings in terms of mechanical work and heat. Before getting started, I want to clarify the definition of system and surroundings. System is part of the world which we have a special interest in, or more specifically, the portion that we single out for study. Surroundings are the region outside the system where measurements are made. For example, a chemical reaction is the system to a chemist studying the particular chemical reaction. Solvent, spectator ions, and reaction vessels are part of surroundings. To an engineer who designs an automobile engine, the system is the engine cylinder, where the mechanical action of the engine occurs by the cycle of gas intake, compression, expansion by combustion, and exhaust. There are three types of systems. An open system is the one that allows the transfer of both matter and energy through the boundary between the system and surroundings. Human body is an example of open system because both energy like body heat and matter like sweat are coming out of the body. A closed system is the one that allows the transfer of the energy through the boundary, but does not allow the transfer of matter. An isolated system is the one that does not allow the transfer of both matter and energy. The universe is an example of the isolated system. There are two types of boundaries that separate the system from the surroundings. Diathermic boundary permits the transfer of heat, but adiabatic boundary does not permit the transfer of heat. Thermodynamic processes can be either exothermic or endothermic, depending the direction of heat flow. An exothermic process is the process that releases heat or thermal energy from the system to its surroundings, causing the temperature of the surroundings to rise, like burning of gasoline. Endothermic process is the one that the system absorbs the heat from the surroundings, causing the temperature of the surroundings to fall, like vaporization of water. The first law of thermodynamics states that the total energy of the universe, or an isolated system, cannot be created nor destroyed. This can be written as a mathematical equation, delta U equals Q plus W. Capital U represents the internal energy of the system. The internal energy is the total kinetic and potential energy of the constituents of the system, like atoms, ions, or molecules. Internal energy is a state function. Take note, a state function is a property with a value that depends only on the current state of the system, and it is independent of how that state has been prepared or independent of the path that the system may take. Examples of state functions are internal energy, enthalpy, entropy, Gibbs free energy, and Helmholtz free energy. Q represents heat, and W represents work. Heat and work are not state functions because the heat transferred and work done depend on the path. Conventionally, the symbol delta is used for a state function and represents change. So delta U is the change of internal energy, or simply U final minus U initial. Let me use an animated illustration to show the difference between state functions and path functions. Here is a battery that is fully charged. Delta U is the total energy of the battery when fully charged. all the energy of the battery can be consumed only for heating. The heat generated in this path of battery usage, or the heat generated in path 1, is denoted by Q1. Obviously, delta U equals Q1. The same battery can be used to power an electric fan. Let's assign this path of battery usage to path 2. The mechanical work done by the fan blades is denoted by W2. The fan also generates heat during the operation. You may feel it when you touch the house of the motor of the fan. The heat in path 2 is denoted by Q2. It implies that the internal energy delta U is consumed to generate heat Q2 and do work W2. It can be written mathematically, delta U equals Q2 plus W2. As you can see, delta U is the same no matter what path the system may choose. That is the reason why delta U is a state function. However, the quantity of thermal energy is different depending on path. The mechanical work in path 1 is 0, but the work in path 2 is non-zero. Since heat and work are path dependent, they are path functions. Where does the internal energy originate? The internal energy is the total kinetic and potential energy of the constituent atoms, ions, or molecules of the system. Please note that a molecule has a certain number of motional degrees of freedom: translation, rotation, and vibration. The translational energy, rotational energy, and vibrational energy to one direction, x, y, or z, are 1/2 mv squared, 1/2 I omega squared, and 1/2 kx squared, respectively. In translational motion, m represents the mass of molecule, v is its velocity. In rotational motion, capital I represents the moment of inertia, and omega is angular velocity. In vibrational motion, k is force constant, and x is the displacement of the oscillator. Classical equipartition theorem states for a particle at thermal equilibrium, the average value of each quadratic contribution to the energy is 1/2 kBt. It implies that every individual motional energy represented by 1/2 mv squared, 1/2 I omega squared, and 1/2 kx squared is equivalent to 1/2 kBt. Keep in mind that the equipartition theorem agrees well with empirical results at high temperature, where quantum effect is not significant, which implies we may have to exclude vibrational motion, where quantum effect is high and not negligible. A perfect gas molecule is conventionally accepted as a spherical molecule. As a result of it, only translational motion is counted to determine the internal energy of perfect gas. Remember, rotating a spherical molecule in any direction does not demand any energy because the molecule does not change its position in the course of rotation. The translational energy along each direction, x, y, or z, is represented by 1/2 mv squared. The sum of the energy in all directions is 3/2 mv squared, which is equivalent to 3/2 kBt based on equipartition theorem. That is the translational energy of a single molecule. What is the translational energy of 1 mole of molecules? You should multiply it by the Avogadro's number, Na. Remember, Boltzmann constant Kb times Avogadro's number, Na, is equal to gas constant, capital R. Consequently, it is simplified to 3/2 RT. And this is the molar internal energy of perfect gas, delta UM. What is the molar internal energy of linear molecules? Like a spherical molecule, It has translational energy 3/2 mv squared, which can be converted to 3/2 kBt utilizing equipartition theorem. In addition to that, the linear molecule has non-zero rotational energy. Suppose a linear molecule lies along the y-axis. Rotating the molecule around the y-axis does not change the positions of the atoms of the molecule. Consequently, the rotational motion around the y-axis does not require any energy. However, rotating the molecule around the x-axis brings about the positional change of the atoms of the molecule. The motional energy that is associated with the rotation is represented by 1/2 I omega squared. For the same reason, the motional energy that is associated with the rotation around the z-axis is also 1/2 I omega squared. Consequently, the sum of rotational energy of a linear molecule is 2/2 I omega squared, which can be converted to 2/2 kBt. You should multiply this by Avogadro's number to get the molar internal energy of the linear molecule, which can be simplified to 5/2 RT. Now, you can easily find the molar internal energy of a nonlinear molecule. What is it? It is 6/2 RT or 3 RT. Expansion work is the work arising from a change in volume. Take note that the expansion work also includes work associated with negative changes of volume of the system, that is, compression. Check this cylindrical chamber closed by a piston. The inside of the chamber is the system. External pressure acts on the piston and pushes the piston down. This causes volumetric change of the system, that is, compression. The change of height of the piston is represented by delta L, and the area of the base is denoted by capital A. Remember, delta L is negative for compression, but positive for expansion. The work is defined by negative force acting on an object times the positional change of the object, delta L. Please note that the negative sign implicates the direction of energy flow. Negative work indicates the system does work to the surroundings, implying energy flows from the system to the surroundings. Positive work indicates the surroundings do work to the system, implying energy flows from the surroundings to the system. You may divide force F by area A, followed by multiplying it by area A. F over A is pressure, which is acting externally, and it is called external pressure. Capital A times delta L is volumetric change, or delta V. In volumetric compression, delta V is negative. This would make work positive due to the negative sign, and it implies that surroundings do work on the system. Positive work also implies the system gains energy from the surroundings, leading to the increase of internal energy. In volumetric expansion, delta V is positive. This would make work negative due to the negative sign, and it implies that the system does work on the surroundings. Negative work also implies the system loses energy to the surroundings, leading to the decrease of internal energy. For the infinitesimal volumetric change, it can be written dW equals negative pressure external times dV. Take note that the differential of a state function like volume is exact because it is path independent, but the differential of a path function like work is inexact because it is path dependent. The work done by or to the system can be written in an integral form like this. Number 1 and 2 represent initial and final states. Integral from state 1 to state 2 dW can be rewritten as negative integral from volume 1 to volume 2 external pressure times dV. We can use this integral to determine the work done under a variety of conditions. Free expansion is the volumetric increase of the system against zero external pressure or vacuum. It implies external pressure is zero. Consequently, the work done under this condition is zero. What about the work done under constant external pressure? Since the external pressure is a constant, it can be taken out of the integral. Integral from V1 to V2 dV is simply V2 minus V1. And it is negative P external times delta V. This is an animation illustrating a volumetric expansion against constant external pressure. This is the initial volume of the system before expansion, which is denoted by V1. A blue dot on the PV plot represents the initial state of the system. Now, the volume of the system is expanding against constant external pressure. The final volume after the expansion is denoted by V2. A red dot on the PV plot represents the final state of the system. The volumetric difference between V1 and V2 is represented by delta V. Then, the work done by the system is equal to negative P external times delta V. And it is the same with the area of the green rectangle on the PV plot. A reversible process is an equilibrium process where the direction of the process to the system or surroundings can be reversed by infinitesimal changes of properties like pressure or temperature. Suppose the system that is made of perfect gas undergoes a reversible volumetric expansion under an isothermal condition. Every step of the expansion is very subtle due to the infinitesimal decrease of pressure between the system and the surroundings. You can say that the internal pressure is almost the same with the external pressure, which can be written as P. This is an integral form that describes expansion work. Like I said, P external is almost the same with P internal under a reversible condition, and P external can be replaced by P. Take note that the pressure P here is not a constant, but a variable, because it continuously varies until the expansion is completed. Consequently, you should not bring it outside the integral. Utilizing the equation of state of perfect gas, pressure can be replaced by nRT over V. Since gas cannot escape the system and the temperature remains constant at an isothermal condition, nRT is a constant as a whole, and you can leave it out of the integral, which is equal to negative nRT times log V2 over V1. And this is the expansion work done under an isothermal reversible condition. Here is an illustration that shows the reversible expansion of a cylindrical chamber. The blue dot on the PV plot represents the initial state of the system, and the red dot represents the final state of the isothermal reversible expansion. Every step in the expansion is in mechanical equilibrium. Take note, as the volume of the gas in the chamber increases from V1 to V2, the pressure of the gas decreases. The area under the curve is the result of integrating the PV work from volume V1 to volume V2, which corresponds to negative nRT times log V2 over V1. Let's compare the work done under an isothermal reversible condition with the work done under an isothermal irreversible condition. Suppose the external pressure is the same with P2. An irreversible process is a non-equilibrium process, where the direction of the process to the system or surroundings cannot be reversed due to the significant difference in pressure or temperature between the system and surroundings. As we learned above, the work done under a reversible condition is the same with the area under the curve in the PV plot. What about the work done under an irreversible condition? Under this condition, the external pressure, which is the same with P2, is substantially smaller than P1. So, the expansion occurs all of a sudden. The work done in this irreversible condition is the area of the blue rectangle, which is equal to negative P2 times delta V. It is obvious that the area under the curve on the left is significantly greater than the area under the horizontal line on the right. It implies that the work done in a reversible condition is always greater than the work done in an irreversible condition. Like I said previously, work is not a state function, but a path function instead. It implies that the work done by the system depends on the path that the system may take. Let me demonstrate it with a pressure-volume plot and a volumetric compression of gas. The initial state of the volumetric compression is represented by this red dot. The red dot I defines the initial pressure and volume. As the gas is compressed, its volume decreases, but its pressure increases instead. The final state is represented by the blue dot. The blue dot F defines the final pressure and volume. Take note that the final pressure is greater than the initial pressure, but the final volume is less than the initial volume. There are many different ways to get to the final state from the initial state. Let me select two paths and call them path 1 and path 2. Path 1 looks like this. The first step of path 1 is made by compressing the volume of the gas from Vi to Vf, while the pressure of the gas is maintained constant to Pi, and the second step is made by increasing the pressure to Pf, while the volume of the gas is maintained constant to Vf. How can the path 1 is created empirically? You may cool the gas, which would lead to volumetric compression from Vi to Vf under the constant pressure Pi. That's step 1. In the subsequent step, you may heat the gas while maintaining the volume constant at Vf until the pressure of the gas increases from Pi to Pf. The work done in path 1 is this. Negative integral from Vi to Vf Pi dV plus negative integral from Vf to Vf P dV. The first integral turns out to be negative Pi times Vf minus Vi. Be aware that the initial pressure Pi is a constant. The second integral is 0. Consequently, the work done in path 1 is negative Pi times Vf minus Vi. The Vf minus Vi is negative because Vf is smaller than Vi. This makes the work positive due to the negative sign in the front. The work done to the gas in the course of compression in path 1 is the same with the area of the shaded rectangle in blue. Let's go back to the first plot. The final state of the compression process can be reached via path 2. The first step of path 2 is made by increasing the pressure to Pf, while the volume of the gas is maintained constant to Vi. And the second step is made by compressing the gas from Vi to Vf, while the pressure of the gas is maintained constant to Pf. How can the path 2 is created empirically? You may heat the gas while maintaining the volume constant at Vi until the pressure of the gas increases from Pi to Pf. That's step 1. In the subsequent step, you may cool the gas, which would lead to volumetric compression from VI to VF under the constant pressure PF. The work done in path 2 is this. Negative integral from VI to VI P dV plus negative integral from VI to VF PF dV. The first integral is 0, and the second integral turns out to be negative PF times VF minus VI. Be aware that the final pressure PF in the second integral is a constant. Consequently, the work done in path 2 is negative PF times VF minus VI. VF minus VI is negative because VF is smaller than VI. This makes the work positive due to the negative sign in the front. The work done to the gas in the course of compression in path 2 is the same with the area of the shaded rectangle in blue. The work done in path 2 is greater than the work done in path 1. This is clearly visualized in the shaded rectangles in both plots. Since the work depends on the path that the system would take, work is not a state function, but a path function. You may combine the two paths after reversing path 2. Then, total work would be like this. The work of path 2 is negative because the path was reversed. So, total work is equal to W1 minus W2. Plug W1 and W2 into the equation like this. This leads to PF minus PI times VF minus VI. Since PF is greater than PI, PF minus PI is greater than 0. Since VF is less than VI, VF minus VI is less than 0. Consequently, total work in this cyclic process is negative as a whole. This negative total work is the net work done to the environment, which is equal to the area of rectangle shaded in blue in the plot. The work of this cyclic process is represented by cyclic integral dW, which is not 0. It is indicative that work is path dependent, and dW is an inexact differential. Take note that the cyclic integral of any state function is 0 because in a cyclic process, it happens that the initial state becomes the final state, and a state function depends only on the initial and final states, not a path. And the differential of a state function is exact. The quantity of heat transferred becomes different when the physical condition of the system changes. As a result of it, it should be denoted differently. It could be either internal energy that is denoted by capital U or enthalpy that is denoted by capital H. The question is what specific physical condition denotes heat to internal energy and what condition denotes heat to enthalpy, and how they are related to each other. Before getting started with this topic, take note of the difference between diathermic condition and adiabatic condition. Diathermic boundary allows heat transfer between the system and the surroundings, but adiabatic boundary does not allow heat transfer. C sub V represents heat capacity at constant volume, and I will show you how the C sub V is related to delta U. Like previously stated, the first law of thermodynamics is expressed mathematically. du equals dq plus dw. Remember, lowercase d represents infinitesimal change, while delta represents sizable change. This equation exhibits the fact that the internal energy of the system can be stored or spent in the form of thermal energy called heat and mechanical work. The work can be non-expansion additional work, which is denoted by W sub E, and expansion work, which is denoted by W sub EXP. Suppose the system undergoes a process at constant volume with no additional work. It implies dW sub E is 0 because there is no additional work involved in the process, and expansion work dW expansion is also 0 because expansion work is negative PdV and dV is 0 due to the condition of constant volume. Now the equation above is simplified to du equals dq or du equals dq sub V. The subscript capital V represents constant volume. For a measurable change, delta U equals Q sub V. Take note that the symbol delta is used for state functions like internal energy, enthalpy, volume, pressure, etc. Heat transferred is directly proportional to temperature change, or delta T. If you use a proportionality constant, C sub V, it can be written as Q sub V equals C sub V times delta T. The C sub V is called calorimeter constant, or heat capacity at constant volume. Measuring heat under the condition of constant volume requires a sophisticated device called bomb calorimeter, as you can see on the right. Bomb is a stainless steel cylindrical container tightly sealed. It is immersed in a water bath. A sample to be analyzed is placed in a boat inside a bomb. A chemical reaction like combustion takes place electrically, leading to the increase of temperature of water outside a bomb. The thermometer placed in the water bath measures the temperature change. Once the heat capacity of the calorimeter is known, you can determine the heat transferred during the reaction using the equation Q sub V equals C sub V times delta T. All electrical energy is equal to heat transferred. That is, Q sub V equals IVT. The unit of current, capital I, is ampere, or capital A. The unit of voltage is volt, or capital V, and the unit of time is second, or lowercase s. AVS is an energy unit, which is equal to joule. Since delta U equals Q sub V and Q sub V equals C sub V times delta T, delta U equals C sub V times delta T. You may modify this equation and express C sub V like this. C sub V equals delta U over delta T. For an infinitesimal change, the C sub V can be also written as partial derivative of U with respect to T. Heat capacity is a physical property of matter that is defined as the amount of heat to be supplied to an object in order to produce a unit change in its temperature. Heat capacity at constant volume is expressed mathematically as the first partial derivative of internal energy with respect to temperature under constant volume condition. It is an extensive property. An extensive property depends on the size of the system or the amount of materials in the system. Examples of extensive properties are volume, mass, and moles. On the contrary, an intensive property does not depend on the size of the system or the amount of materials in the system. Examples of intensive properties are pressure, temperature, density, molar quantities like molar volume, molar mass, molar enthalpy, and concentrations like molarity, molality, ppm, and ppb. Check the definition of heat capacity at constant volume. In this expression, internal energy is an extensive property because it depends on the quantity of materials in the system. However, temperature is an intensive property because it does not depend on the size of the system. And the heat capacity is an extensive property. Be aware that molar heat capacity is the heat capacity of 1 mole of a substance, and it is an intensive property. Both C sub V and moles are extensive properties. Consequently, C sub Vm, or molar heat capacity, becomes an intensive property. Take note, if you divide an extensive property by another extensive property, the result always becomes an intensive property. Specific heat capacity, or simply specific heat, is a particular type of heat capacity, and it is defined as heat capacity per unit mass. Specific heat of water is well known as 4.184 joules per Kelvin per gram. Heat capacity will be taken as independent of temperature unless otherwise stated. You may ask a question like, what is the observable difference between the material with large heat capacity and the material with small heat capacity? The answer is pretty obvious. The material with large heat capacity would increase its temperature less than the one with small heat capacity when the same quantity of heat is added. It is the reason why the material with high heat capacity is used for thermal insulation. Now, this is a different issue about the heat capacity. At phase transition, like melting or vaporization, temperature remains the same or delta T is 0. Remember, delta T is positioned at the denominator of the mathematical expression of heat capacity. As a result of it, C sub V is infinite at phase transition. We learned previously how delta U and C sub V are related, and we also learned that delta U is a form of heat. But there is another form of heat called enthalpy, which is denoted by capital H. In the previous slide, I mentioned that heat transferred at constant volume is internal energy, and when the volume is changing, heat transferred, or dQ, is not equal to internal energy. Here comes new form of heat called enthalpy. Enthalpy is defined as internal energy plus pressure times volume, or capital U plus P times V. How can the change of enthalpy be described by internal energy, pressure, and volume? To answer that, we should take a derivative on both sides of the equation like this. Now the right side would be du plus dpv. The dpv can be written out to v dp plus p dv by applying the product rule. I hope you remember that du equals dq plus dw, and the dw is equal to negative p dv. Plug this into the equation above. Then, the equation can be written out to dH equals dq minus pdv plus vdp plus pdv. The pdv's are cancelled. Now dH is simplified to dq plus vdp. At constant pressure with no additional work, dH equals dq sub p. For a sizable change, delta H equals Q sub p. It implies that the heat transferred at constant pressure is enthalpy. In summary, the heat transferred at constant volume is internal energy, or delta U, and the heat transferred at constant pressure is enthalpy, or delta H. Calorimetry can be performed at constant volume and at constant pressure. Isometric calorimetry is the calorimetry performed at constant volume, while isobaric calorimetry is the one performed at constant pressure. The heat measured in the isometric calorimetry is internal energy, and the heat measured in the isobaric calorimetry is enthalpy. The device to be used in calorimetry is called calorimeter. The one that provides constant volume condition is bomb calorimeter. The one that is widely used in the general chemistry laboratory is coffee cup calorimeter, and it works at constant pressure. It is suitable for isobaric calorimetry as long as good thermal insulation is in place in order to minimize heat loss. Let me show you how enthalpy and internal energy are related. In previous slide, enthalpy was defined as internal energy plus pressure times volume. Place delta on both sides of the equation like this, which will be delta U plus delta PV. At this point, we should treat the equation differently depending on whether we are dealing with gas or condensed phase like solid and liquid. For the sake of gas, delta PV can be modified to delta nRT utilizing the perfect gas equation. Under constant temperature condition, RT is a constant as a whole, so you may leave it out like this. It implies that the delta H for a reaction that involves the production or consumption of gas is the sum of delta U and the change of moles of gas times RT. Take note that delta N sub G represents the change in the moles of gas molecules before and after the reaction. On the contrary, we should handle the equation differently for solid and liquid. It is because there is almost no volumetric change in the reaction that involves only solid or liquid or both. The delta PV can be written out to P delta V plus V delta P utilizing the product rule. Under constant pressure condition, delta P is 0, and the delta H is simplified to delta U plus P delta V. Since there is almost no change in volume in the reaction that involves only solid or liquid or both, delta V can be approximated to 0. Consequently, delta H is almost the same with delta U. The heat transferred at constant pressure is enthalpy. This statement is expressed mathematically. dH is equal to dQ sub P, which is equal to C sub P times dt. You may divide both sides of the equation by moles. Then it becomes dH sub m equals C sub Pm times dt. C sub P represents the heat capacity at constant pressure, and C sub Pm represents the molar heat capacity at constant pressure. Experimental heat capacity is actually temperature dependent. Here is empirical molar heat capacity at constant pressure, which is equal to A plus Bt plus C over T squared. A, B, and C are temperature-independent constants. In order to determine the sizable change of enthalpy in a range of temperature, you should take integral on both sides of this equation. That is, molar delta H equals integral from T1 to T2 C sub Pm dt. Plug the C sub Pm into the equation. The results of the integration is this. It is slightly complex and tricky to handle empirical heat capacity to determine delta H of a reaction. The difference between the heat capacity at constant pressure and the heat capacity at constant volume is nR. Likewise, the difference between the molar heat capacity at constant pressure and the molar heat capacity at constant volume is R. I will prove this on the later of this chapter. Let's take a look at how the internal energy of the system is expressed at a particular condition called reversible adiabatic condition. Since heat is not transferred in a reversible adiabatic process, Q is 0, which leads delta U to being equal to the expansion work W or W adiabatic. We know that work is not a state function. However, the work done at a reversible adiabatic condition is a state function because it is equal to delta U, and delta U can be expressed as C sub V times delta T, which was derived in the previous slide. In this slide, I will show you why delta U is equal to C sub V times delta T in a reversible adiabatic process. This is a temperature volume plot. Suppose a gas in a cylinder undergoes a reversible adiabatic expansion. The initial state of the expansion is represented by this red dot, and it defines the initial temperature and volume. As the volume of the gas is expanded from Vi to Vf, the temperature of the gas decreases from Ti to Tf. The blue dot represents the final state of the expansion, and it defines the final temperature and volume. You may ask yourself, how come it gets cool when a gas expands? I will tell you a good real-life example. If the air pressure in one of the tires of your vehicle is too high, you have to get the air out until the pressure is reduced to the optimum pressure value. If that happens on a hot summer day, touch the air inlet. You would feel cool from it. The rubber enclosure of the tire makes an adiabatic condition somehow, even if it is still far from being perfectly adiabatic. This entire expansion process can be split into two steps. Step 1 is made by increasing the volume from Vi to Vf, while the temperature is maintained constant to Ti. Step 2 is made by decreasing the temperature from Ti to Tf, while the volume is maintained constant to Vf. The internal energies in step 1 and step 2 are represented by delta U1 and delta U2. Take note, delta U is 0 at constant temperature. Consequently, delta U1 is equal to 0. When the temperature changes at constant volume, delta U is equal to C sub V times delta T. Consequently, delta U2 is equal to C sub V times delta T. Now, the overall delta U is equal to C sub V times delta T. Now, let's see how pressure and volume are related at a reversible and adiabatic condition. Infinitesimal change of internal energy at a reversible adiabatic condition can be written like this. The dW adiabatic represents the expansion work done at a reversible adiabatic condition, and it is equal to negative P dV. du can be also written Cv dt. It is obvious that Cv dt equals negative P dV. Modify the perfect gas equation with respect to pressure and plug it into the equation like this. Now, we have Cv dt over T equals negative nR dV over V. In order to find the change from the initial and the final states, you should integrate both sides of the equation like this. Take note that both Cv and nR are constants and can be taken out of the integral. The result of the integration is Cv log Tf over Ti equals negative nR log Vf over Vi. Move nR to the left side of the equation. Negative log Vf over Vi can be rewritten as log Vi over Vf. You may remove the negative sign by flipping the fraction inside a log. Since Cv over nR is a constant as a whole, you can replace it with a single constant C in the equation. Now the constant C can be brought inside a log as an exponent like this. The logs on both sides of the equation are equal. That means Tf over Ti to the power of C equals Vi over Vf. As we defined constant C just before, it is Cv over nR. Previously, I mentioned that the difference between the heat capacity at constant pressure Cp and the heat capacity at constant volume Cv is nR. The constant C can be expressed as Cv over Cp minus Cv. Divide both numerator and denominator by Cv. It would lead to 1 over Cp over Cv minus 1. Define gamma as Cp over Cv. In other words, gamma is the ratio of Cp to Cv. Because Cp is greater than Cv in magnitude, gamma is always greater than 1. Now, the constant C can be expressed as 1 over gamma minus 1. Plug this into the equation, and it will lead to this. Now, raise both sides of the equation to the power of gamma minus 1, which would lead to this. The exponent, gamma minus 1, can be distributed to both numerator and denominator like this. Rearrange the equation like this. TIVI to the power of gamma minus 1 equals TFVF to the power of gamma minus 1. It implies that TV to the power of gamma minus 1 is always the same in a reversible adiabatic condition, no matter what state the system is positioned. Now, use this equation that was derived just before and find how the pressure and volume are related under a reversible adiabatic condition. Modify the perfect gas equation with respect to temperature and plug it to the equation like this. Simplify Vi times Vi to the power of gamma minus 1. Simplify Vf times Vf to the power of gamma minus 1. This leads to Pi Vi to the power of gamma over Nr equals Pf Vf to the power of gamma over Nr. The Nr's are cancelled. So, we have Pi Vi to the power of gamma equals Pf Vf to the power of gamma. It implies that Pv to the power of gamma is always the same, or gives a constant value in a reversible adiabatic condition, no matter what state the system is positioned. In summary, under a reversible adiabatic condition, Tv to the power of gamma minus 1 gives a constant value, and Pv to the power of gamma also gives another constant value regardless of the physical state of the system. Under a reversible isothermal condition, the pressure and volume of gas are inversely proportional to each other, or pressure times volume gives a constant value, or the pressure of gas is directly proportional to 1 over V. This is the famous Boyle's law. However, under a reversible adiabatic condition, pressure times volume to the power of gamma gives a constant value regardless of the physical state of the system, or the pressure of gas is directly proportional to 1 over V to the power of gamma. The gamma is Cp over Cv, which is greater than 1. We can plot these two on the pressure-volume plot. Under a reversible isothermal condition, the pressure and volume of gas generates a hyperbolic curve like this, illustrating the inversely proportional relationship between pressure and volume. This PV curve at constant temperature is called isotherm. How about PV curve under a reversible adiabatic condition? Take note of the power gamma that the volume is raised to. Since gamma is greater than 1, 1 over V to the power of gamma is smaller than 1 over V, which would place the curve below the isotherm. This PV curve at an adiabatic condition is called adiabat. Thermochemistry is the area of chemistry that is associated with heat transfer in the course of chemical reactions. Standard state is a physical state that we often refer to in order to determine the properties of materials under different physical states. Standard enthalpy change is denoted by delta H, and standard state symbol, which is a crossed circle positioned at the right top corner. It is the enthalpy change under the standard states at the pressure of 1 bar and temperature of 25 Celsius. Standard enthalpy of physical changes like vaporization, sublimation, and fusion can be represented by this notation. Here is a diagram that illustrates the phase changes of a substance. Heating solid causes it to melt to liquid. Continuous heating would cause it to vaporize to gas. However, under a specific condition, the solid may sublimate directly to gas. The heat associated with melting is called enthalpy of fusion. The heat associated with vaporization is called enthalpy of vaporization, and the heat associated with sublimation is called enthalpy of sublimation. The enthalpy of sublimation is the sum of enthalpy of fusion and the enthalpy of vaporization, which is manifest in the diagram. Like I said previously, enthalpy is a state function that does not depend on the path that the system may take, but it only depends on the initial and final states. Reversing a chemical reaction implies that the reactants becomes products and products becomes reactants. It further implies that the initial state becomes the final state and the final state becomes initial state. Consequently, the sign of enthalpy of the reverse reaction is changed. Standard reaction enthalpy is the enthalpy change or heat that is transferred in a chemical reaction at the standard states. Standard formation enthalpy is a specific standard reaction enthalpy, that is, the standard reaction enthalpy for the formation of 1 mole of a compound from its elements in their reference states. Take note that the reference state of an element is the most stable state of the element at specific temperature and 1 bar. For instance, the reference state of nitrogen is gaseous molecular nitrogen. The reference state of mercury is the mercury in the liquid phase. And the reference state of carbon is solid graphitic carbon. Be aware that element carbon present in nature is most likely in the form of crystalline graphite, crystalline diamond, or amorphous carbon like soot. Out of those multiple states of carbon, the graphitic carbon is the reference state because it is the most stable state. Take note that the standard formation enthalpies of all elemental forms are 0 at all temperature. The standard formation enthalpy of proton in an aqueous solution is also 0. Standard formation enthalpies are so versatile for the determination of the standard reaction enthalpy of any chemical reaction, which is equal to the sum of the formation enthalpies of products minus the sum of the formation enthalpies of reactants. The standard formation enthalpies of most elements and compounds can be found at the resource section at the end of the textbook. The nu and nu prime are the stoichiometric coefficients of products and reactants. Here is a chemical reaction. Reactants A and B react by 2:1 mole ratio and produce products C and D by 3:1 mole ratio. Determine the standard reaction enthalpy of this reaction. The formation enthalpies of A, B, C, and D are given. Plug the formation enthalpy values into the equation. Don't forget the stoichiometric coefficients. This would lead to the standard reaction enthalpy of the reaction. Hess's law states the standard enthalpy of an overall reaction is the sum of the standard enthalpies of the individual reactions into which a reaction may be divided. Here is a practice problem that is associated with the Hess's law. Pause the video and use these three individual reactions and their reaction enthalpies and determine the enthalpy for the overall reaction at the bottom. Keep it in mind, if a reaction is reversed, the sign of the enthalpy should be changed because enthalpy is a state function. If a reaction is multiplied by a certain factor, the enthalpy of the reaction should be also multiplied by the same factor. Use the first reaction and its reaction enthalpy as is. Reverse the second reaction. Don't forget to change the sign of the reaction enthalpy. And then multiply both by 1/2. Move to the third reaction. Multiply the third reaction and its reaction enthalpy by 1/2. Combine all three reactions and the three reaction enthalpies. This leads to the overall reaction and its reaction enthalpy. Kirchhoff's law describes the temperature dependence of the enthalpy of a reaction. It is expressed mathematically like the reaction enthalpy at temperature T2 equals the reaction enthalpy at T1 plus integral from T1 to T2 delta Cp of the reaction times dt. The delta Cp of the reaction is simply the sum of molar Cp's of products minus the sum of molar Cp's of reactants. Nu and nu prime are the stoichiometric coefficients of products and reactants. The differentials of state functions are exact, which means an infinitesimal quantity which when integrated gives a result that is independent of the path between the initial and final states of the system. This allows us to determine the change of internal energy or any other state function at the variation of physical state of the system, which is represented by integral from initial state to final state du, which is equal to u final minus u initial. On the contrary, differentials of heat or work are inexact, which means an infinitesimal quantity which, when integrated, gives a result that depends on the path between the initial and final states of the system. It is the reason why heat and work are not state functions. Suppose the internal energy of the system depends on both volume and temperature. In other words, there are two variables, volume and temperature, that change the internal energy. This is an illustration about the volume and temperature dependence of internal energy. Imagine a device that is made to measure the internal energy of the system in joules. It has two knobs to control the volume and temperature of the system by ramping up or down, which allows us to observe the change of internal energy. You can either maintain the volume or pressure constant while the other variable is changing. Constant volume means you can only ramp up or down the temperature. This plot shows how internal energy changes as temperature changes. Red dot I represents initial state. As temperature is ramped up, the internal energy increases until the system reaches the final state, which is represented by the blue dot. Suppose the temperature difference between Tf and Ti is infinitesimally small, which is represented by dt. Likewise, the corresponding internal energy difference is also infinitesimally small, which is represented by du. This red straight line represents the slope of the curve at this narrow range, which is almost a single spot. The slope is du over dt. Since we have two independent variables, volume and temperature, and volume is maintained constant, we should use the rounded d representing partial derivative. That is, partial derivative of internal energy with respect to temperature at constant volume. U final can be expressed as U initial plus du. du can be written as partial derivative of u with respect to t at constant volume times dt. Take note that the rounded dt of the slope is cancelled by dt, which makes the equality valid. Now, you can maintain the temperature constant during a volumetric expansion of the system, and the internal energy of the system decreases because of the work done to the surroundings. This process is illustrated by this plot. Take note that infinitesimally small increase of volume, dV, causes infinitesimally small decrease of internal energy, du. Like we did for the constant volume case, U final can be expressed as U initial plus partial derivative of U with respect to V at constant t times dt. Be aware of how the slope is represented by the first partial derivatives at constant volume and constant temperature. Now, how do we represent the final internal energy when both volume and temperature are changing? It is not hard at all. It is like you are ramping up or down both temperature and volume knobs of the device simultaneously. You should include both partial derivatives like this. Move U initial to the left side of the equation. The difference between U initial and U final is infinitesimally small, which is represented by du. Now, we end up with this equation. du equals partial derivative of u with respect to v at constant t times dv plus partial derivative of u with respect to t at constant v times dt. This is called the total differential of internal energy that has variables of volume and temperature. The first slope is the partial derivative of u with respect to v at constant t. It is called internal pressure because it ends up with a pressure unit and it is represented by pi t. How about the second slope? Don't you think it is familiar? Pause the video and guess what it is. It is the heat capacity at constant volume, which is denoted by Cv. The total differential of internal energy can also be expressed as pi t dV plus Cv dt. Let's try some practice. Enthalpy is a state function that has variables, pressure and temperature. Pause the video and write the total differential of enthalpy. The answer is this. Take note of the two slopes, which corresponds to two knobs of the device of measuring enthalpy, pressure knob and temperature knob. Here is another example. Assume function f is a state function, and it has three independent variables. So, unlike internal energy or enthalpy, it has one more variable, right? Pause the video and write the total differential of the function f. The answer is this. Be aware of the three slopes, which represent three knobs of the device that measures the value of function f. One take-home lesson is that if a function has more than two independent variables, you should use individual partial derivatives of the function in order to write its total differential. Partial derivative is like pick one variable and get the derivative with respect to that variable only, while other variables are kept constant. Maxwell relation can be found from the total differential of a state function, and it is very useful for problem solving. So, you should know how to write it when a state function and its variables are given. Let me use a function f that has two independent variables, x and y. First, pause the video and write the total differential of function f. It is df equals partial derivative of f with respect to x at constant y times dx plus partial derivative of f with respect to y at constant x times dy. Take the first slope and get the first partial derivative of the first slope with respect to the second variable y. And then take the second slope and get the first partial derivative of the second slope with respect to the first variable x. It is like y derivative of x derivative of f is equal to x derivative of y derivative of f. This mathematical relation can be applied to all state functions like internal energy, enthalpy, Gibbs free energy, and Helmholtz free energy. This is called Maxwell relation. Now, do you think you're ready to write the Maxwell relation of internal energy with variables of volume and temperature? Pause the video and write it down. And it is T derivative of V derivative of U is equal to V derivative of T derivative of U. I will talk more about the Maxwell relation later. In this and the following slides, I will show you how to write the differentials of internal energy, enthalpy, Gibbs free energy, and Helmholtz free energy when each of them has two independent variables. I will also show you how to find the Maxwell relation of each function. Like I said previously, the differential of a state function is exact, which implies that the function is independent of the path that the system may take. The differential of internal energy is du equals dq plus dw. The expansion work dw is equal to negative pdv. So you can plug it into the equation like this. I have not covered the thermodynamic definition of entropy, but it is dq over t. Modify the equation with respect to dq, which is dq equals tds. Plug it into the equation like this, which leads to du equals tds minus pdv. Take note of ds and dv in the equation. This implies that internal energy U can also be a function of entropy and volume. Now pause the video and write the total differential of the internal energy that has variables of entropy and volume. It should be this one. Compare these two differentials. ds and dv are present in both equations, which implies that the partial derivative of u with respect to s is equal to t, and the partial derivative of u with respect to v is equal to negative p. Check the total differential of internal energy above. Take note that internal energy is a function of two independent variables, entropy and volume. Now, you will be able to write the Maxwell relation of internal energy, U. Pause the video and write it down on a piece of paper. It should be like this. As you can easily notice, the derivative of U with respect to S is equal to T, and the derivative of U with respect to V is equal to negative P. Plug this into the Maxwell relation. It leads to the partial derivative of t with respect to v at constant s equals negative partial derivative of p with respect to s at constant v. This is another form of Maxwell relation of internal energy. Be aware that all four functions, internal energy, enthalpy, Gibbs free energy, and Helmholtz free energy, have their own Maxwell relations like this one. Let's try enthalpy this time. Enthalpy is defined as U plus PV. Differentiate both sides of the equation. Use the product rule for dPV, which is VdP plus PdV. Replace du with TdS minus PdV, which was derived previously. It makes dH equals TdS minus PdV plus VdP plus PdV. PdVs are cancelled. This leads to dH equals TdS plus VdP. Take note of ds and dP in the equation. This implies that enthalpy H is a function of entropy and pressure. Now, pause the video and write the total differential of the enthalpy that has variables of entropy and pressure. It should be this one. Compare these two differentials. ds and dP are present in both equations, which implies that the partial derivative of H with respect to S is equal to T, and the partial derivative of H with respect to P is equal to V. Check the total differential of enthalpy above. Take note that enthalpy is a function of two independent variables, entropy and pressure. Now, you will be able to write the Maxwell relation of enthalpy H. Pause the video and write it down. It should be like this. As you can easily notice, the derivative of H with respect to S is equal to T, and the derivative of H with respect to P is equal to V. Plug these into the Maxwell relation. It leads to the partial derivative of T with respect to P at constant S equals the partial derivative of V with respect to S at constant P. This is another form of Maxwell relation of enthalpy. Let's try Gibbs free energy. Gibbs free energy is defined as H minus Ts. Differentiate both sides of the equation. Use the product rule for dTs, which is negative TdS minus SdT. Replace dH with TdS plus VdP, which was derived previously. It makes dG equals TdS plus VdP minus TdS minus SdT. TdS is cancelled out. This leads to dG equals VdP minus SdT. Take note of dP and dt in the equation. This implies that Gibbs free energy is a function of pressure and temperature. Now, pause the video and write the total differential of the Gibbs free energy that has variables of pressure and temperature. It should be written like this. Compare these two differentials. dP and dt are present in both equations, which implies that the partial derivative of G with respect to P is equal to V, and the partial derivative of G with respect to T is equal to negative S. Check the total differential of Gibbs free energy above. Take note that Gibbs free energy is a function of two independent variables, pressure and temperature. Now, you will be able to write the Maxwell relation of Gibbs free energy G. Pause the video and write it down. It should be like this. As you can see, the derivative of G with respect to P is equal to V, and the derivative of G with respect to T is equal to negative S. Plug these into the Maxwell relation. It leads to the partial derivative of V with respect to T at constant P equals negative partial derivative of S with respect to P at constant T. This is another form of Maxwell relation of Gibbs free energy. Let's try Helmholtz free energy. Helmholtz free energy is defined as U minus Ts. Differentiate both sides of the equation. Use the product rule for dTs, which is negative TdS minus SdT. Replace du with TdS minus PdV, which was derived previously. It makes dA equals TdS minus PdV minus TdS minus SdT. TdS is cancelled out. This leads to dA equals negative PdV minus SdT. Take note of dV and dt in the equation. This implies that Helmholtz free energy A is a function of volume and temperature. Now, pause the video and write the total differential of the Helmholtz free energy that has variables of volume and temperature. It should be written like this. Compare these two differentials. dV and dt are present in both equations, which implies that the partial derivative of A with respect to V is equal to negative P, and the partial derivative of A with respect to T is equal to negative S. Check the total differential of Helmholtz free energy above. Take note that Helmholtz free energy is a function of two independent variables, volume and temperature. Now, you will be able to write the Maxwell relation of Helmholtz free energy. Pause the video and write it down. It should be like this. As you can see, the derivative of A with respect to V is equal to negative P, and the derivative of A with respect to T is equal to negative S. Plug these into the Maxwell relation. The negative signs on both sides are cancelled. It leads to the partial derivative of P with respect to T at constant volume equals the partial derivative of S with respect to V at constant T. This is another form of Maxwell relation of Helmholtz free energy. These four differentials and their Maxwell relations are very useful for problem solving, and consequently, you should keep them in your mind. I briefly mentioned about the internal pressure previously. Do you remember what it is? Suppose internal energy is a function of two independent variables, volume and temperature. The total differential is written like this. The first slope is the partial derivative of U with respect to V at constant T. It is called internal pressure because it has a pressure unit, and it is denoted by pi t. The question is, what is the internal pressure of perfect gas? How about the internal pressure of van der Waals gas? Are they different or the same? Modify the expression of pi t as following. du in the differential of u and the rounded du in pi t are the same. So, you can replace the du with TdS minus PdV. The pi t can be written as t times the partial derivative of S with respect to V at constant t minus p times the partial derivative of V with respect to V at constant t. dV is cancelled out. Now, the pi t is simplified to t times the partial derivative of S with respect to V at constant t minus p. Here is a problem. The entropy in the partial derivative is not a physically measurable quantity. So, we should find a way to replace the derivative with the one that is made up of physically measurable quantities. Here comes the significant role of Maxwell relation. The partial derivative of S with respect to V at constant t is equal to the partial derivative of P with respect to t at constant V. The P and V are physically measurable. Now, the pi t can also be written as t times the partial derivative of P with respect to t at constant V minus P. Modify the perfect gas equation with respect to P and plug it into the equation like this. Since the V in the square bracket is a constant, and moles in a closed system is also a constant, and R over V is a constant as a whole. As a result, you may bring it out of the partial derivative. The partial derivative of t with respect to t is obviously equal to 1. That leads to nRT over V minus P. The nRT over V is simply equal to P. So, P minus P which is 0. So the pi T of perfect gas is 0. Here is the important conclusion that you can draw from it. The fact that pi T is 0 implies that the internal energy of perfect gas never changes during volumetric expansion or compression as long as the temperature remains constant. Let's find out the internal pressure of van der Waals gas. Follow the same procedure that we did for perfect gas up to this far, which is T times the partial derivative of P with respect to T at constant V minus P. Modify the van der Waals equation with respect to pressure and plug it into the equation, which will be led to this. Distribute T derivative to both terms. Be aware that what's inside the square bracket is under the condition of constant volume. Consequently, n squared A over V squared of the second term is a constant, and the first partial derivative of it with respect to T is 0. And nR over V minus NB of the first term is another constant as a whole. So you may bring it out of the derivative. The partial derivative of T with respect to T is 1. This leads to nRT over V minus NB minus P. Plug P of the modified van der Waals equation, which is equal to n squared A over V squared. Be aware that N, A, and V are all positive, which makes the internal pressure of van der Waals gas positive. The volumetric expansion of van der Waals gas makes dV positive at constant temperature. Consequently, in order for the internal pressure to be positive, the dU should be positive. This implies the presence of intermolecular attractive forces of the van der Waals gas. Gases respond profoundly to changes in temperature, whereas solids and liquid will have more modest responses to changes in temperature. Expansion coefficient is defined as the fractional change in volume with respect to the change in temperature. It is denoted by alpha and mathematically expressed as 1 over V times first partial derivative of V with respect to T at constant P. A large value of alpha means that the volume of the sample responds strongly to changes in temperature. The expansion coefficient is an important property in many engineering and scientific applications, such as in the design of heat exchangers, pipes, and containers. Gases are also very compressible, so when subjected to high pressures, their volumes decrease significantly. Be aware that solids and liquids are not as compressible as gases. Isothermal compressibility is defined as the fractional change in volume with respect to the change in pressure, while the temperature remains constant. It is denoted by kappa T and mathematically expressed as negative 1 over V times first partial derivative of V with respect to P at constant T. The negative sign is used here simply to make the isothermal compressibility value positive, because an increase of pressure implying a positive dP brings about a reduction of volume, a negative dV. The isothermal compressibility is also an important property in many engineering and scientific applications, such as in the design of pressure vessels, compressors, and pipelines. It can also be used to describe the behavior of materials in thermodynamic systems. Now, let's find out the expansion coefficient and the isothermal compressibility of perfect gas. Modify the equation of state for perfect gas with respect to volume and plug it into the expression for alpha. Since pressure is maintained constant and gas cannot escape the system, and R over P is a constant as a whole. So it can be brought out of the derivative. dt over dt is simply equal to 1, which leads to nR over PV. Utilizing the equation for perfect gas, this can be further simplified to 1 over T. It shows that the expansion coefficient of perfect gas is simply 1 over T. Pause the video and find the isothermal compressibility of perfect gas by yourself. Use the same method that I did for the expansion coefficient. Modify the equation of state for perfect gas with respect to volume and plug it into the expression for kappa T. Since temperature is maintained constant and gas cannot escape the system, nRT is a constant as a whole. So it can be brought out of the derivative d1 over P over dP is equal to negative 1 over P squared, which leads to nRT over P squared times V. It can be rewritten to nRT over PV times 1 over P. The nRT over PV is 1. Consequently, the isothermal compressibility of perfect gas is simply 1 over P. Suppose a system is under constant pressure. The change in the internal energy of the system depends on the volume and temperature of the system. The total differential of the system can be written like this. The first partial derivative of U with respect to V at constant T is the internal pressure, which is denoted by pi T. The first partial derivative of U with respect to T at constant V is the heat capacity at constant V, which is denoted by CV. Consequently, the differential of internal energy can be written as pi T dV plus CV dt. Both sides of the equation can be divided by dt. Keep in mind that the system is under constant pressure. Now, the equation can be modified like this. The expression for the expansion coefficient can be modified with respect to dV over dt at constant pressure, which is alpha V. This can be plugged into the equation, which leads to alpha pi T V plus CV. Keep in mind that all alpha pi T V and CV are physically measurable parameters. This allows you to determine the rate of change of internal energy with respect to temperature when pressure is held constant. What is the numerical difference between Cp and Cv of perfect gas? As we derived on the previous slide, the first partial derivative of U with respect to T at constant P is equal to alpha pi T V plus Cv. Since pi T of perfect gas is equal to 0, the first partial derivative of U with respect to T at constant P is simply equal to Cv. This is interesting because the definition of Cv is the first partial derivative of U with respect to T at constant V. This illustrates that the Cv is equal to the first partial derivative of U with respect to T either at constant volume or at constant pressure, as long as the gas behaves like a perfect gas. The numerical difference between Cp and Cv is equal to the first partial derivative of H with respect to T at constant P minus the first partial derivative of U with respect to T at constant V. As we just proved, the first partial derivative of U with respect to T at constant V is equal to the first partial derivative of U with respect to T at constant P. So we can replace the derivative with the first partial derivative of U with respect to T at constant P. Since enthalpy is defined as U plus PV, it can be written as the first partial derivative of U with respect to T at constant P plus P times the first partial derivative of V with respect to T at constant P minus the first partial derivative of U with respect to T at constant P. The first and third terms are cancelled. So Cp minus Cv is equal to P times the partial derivative of V with respect to T at constant P. The volume of perfect gas is equal to nRT over P. Since nR over P is a constant as a whole, it can be brought out of the derivative, and the first partial derivative of T with respect to T is 1. Now, P is cancelled out, which leads to nR. Consequently, the numerical difference between Cp and Cv of perfect gas is equal to nR. N is the moles of gas, and capital R is the gas constant. Then what is the difference between Cp and Cv of a gas in general, regardless of whether the gas behaves like perfect gas or not? The Cp can be written as the first partial derivative of H with respect to T at constant P like this. Like I said previously, enthalpy is defined as U plus PV. This will lead to the first partial derivative of U with respect to T at constant P plus P times the first partial derivative of V with respect to T at constant P minus Cv. The first term can be replaced by alpha pi t V plus Cv. The Cv is cancelled out. The expression for the expansion coefficient alpha can be modified with respect to the first partial derivative of V with respect to T at constant P, which is alpha V. This can be plugged into the equation, which leads to alpha pi t V plus alpha PV. Alpha V can be factored out, and it can be written as alpha times pi t plus P times V. The internal pressure pi t is defined previously as the first partial derivative of U with respect to V at constant T. The differential of U is equal to T ds minus P dV. This can be split into two terms, T times the first partial derivative of S with respect to V at constant T minus P. Use the Maxwell relation and replace the derivative, and it will be T times the first partial derivative of P with respect to T at constant V minus P. Euler's chain relation is known as a cyclic chain rule or a triple product rule, and it relates partial derivatives of three independent variables. It is a very useful tool for problem solving. Here are three independent variables: pressure, temperature, and volume. You may begin with any partial derivative. Let's begin with the first partial derivative of P with respect to T at constant V. The next two partial derivatives after the first one should be constructed in this order. You may select any three variables and construct the Euler's chain relation. The product of the three derivatives is equal to -1. Replay this portion of video and learn how to write the Euler's chain relation once three independent variables are given. It is like a snake is biting its own tail. It seems complicated at first, but once you practice enough, you can write the relation easily when you are given with any three variables. This is called Euler's chain relation. The Euler's chain relation can be modified with respect to dP over dt. The dt over dV can be brought to the numerator by taking the reciprocal of it. Do you remember the mathematical expressions for expansion coefficient alpha and isothermal compressibility kappa T? The fraction of these derivatives is simply alpha over kappa T. Plug this to the modified expression of pi T. This will lead to alpha T over kappa T minus P. Plug this to the equation illustrating the difference between Cp and Cv. Pressure is cancelled out. Consequently, the difference between Cp and Cv of any gas in general, including perfect gas, is alpha squared Tv over kappa T. Suppose a gas undergoes a throttling process under an adiabatic condition. I mean, the gas expands rapidly through a small opening from a region of high pressure to a region of low pressure. In this process, the gas experiences a pressure drop, and the temperature of the gas changes as a result of the pressure drop. This phenomenon is called Joule-Thomson effect. I will prove that this adiabatic throttling process is isenthalpic, meaning enthalpy remains constant before and after the process. I will also introduce the Joule-Thomson coefficient. It is the central to the technological issues that are associated with the liquefaction of gases. Here is a cylindrical container. There is a barrier with a small opening in the middle of the cylinder. A piston is installed on each side of the cylinder. The whole cylinder is thermally insulated to provide an adiabatic environment. Consequently, there is no heat transfer between the system and the surroundings. The pressure of the gas on the left side of the cylinder is higher and is about to expand through a small opening on the barrier to the right side of the cylinder. The initial pressure, volume, and temperature before the throttling process are denoted by Pi, Vi, and Ti respectively. The piston on the left side is pushed in, and this causes the gas to be compressed. The gas escaped through a small opening pushes out the piston on the right side. The final volume of the gas is denoted by Pf, Vf, and Tf respectively. The internal energy change of this whole process is denoted by delta U, which is equal to Q plus W. Since this process is carried out under an adiabatic condition, there is no exchange of heat with the surroundings. It further implies that only the mechanical work done is responsible for the temperature change. The work done during the whole process is equal to the sum of the work done at step 1 and step 2. Step 1 is the compression of the gas on the left side of the cylinder, and W1 can be expressed as negative Pi times volumetric change, which is 0 minus Vi. Take note that the final volume in step 1 is 0. Now, W1 is equal to Pi Vi. Step 2 is the expansion of the gas on the right side of the cylinder, and W2 can be expressed as negative Pf times volumetric change, which is Vf minus 0. Take note that the initial volume in step 2 is 0. Now, W2 is equal to negative Pf Vf. Combine the work done in both steps, that is Pi Vi minus Pf Vf. Delta U is Uf minus Ui. Move Ui to the right side of the equation and move negative Pf Vf to the left side of the equation. This leads to Uf plus Pf Vf equals Ui plus Pi Vi. It implies that U plus PV of the initial state equals U plus PV of the final states. U plus PV is enthalpy. It further implies that enthalpy before and after the process remains the same. It proves the fact that this adiabatic throttling process is isenthalpic. Joule-Thomson coefficient is defined as the first partial derivative of T with respect to P at constant enthalpy, which is denoted by mu. It describes the change of temperature of a gas as it undergoes a throttling process experiencing a pressure drop. Suppose enthalpy is a function of two independent variables, pressure and temperature. The total differential of enthalpy can be written like this. Focus on the first slope, or the first partial derivative of H with respect to P at constant T. Write the Euler's chain relation that begins with the first partial derivative of H with respect to P at constant T, which should be this one. Move the last two derivatives to the right side of the equation. Move the two derivatives in the denominator to the numerator by taking the reciprocals of them. The first one is the Joule-Thomson coefficient, which is denoted by mu, and the second one is the heat capacity at constant P, or Cp. So, the first partial derivative of H with respect to P at constant T is equal to negative mu times Cp. Plug this into the total differential of enthalpy, which will lead to negative mu Cp dP plus Cp dt. The negative mu Cp is newly defined as isothermal Joule-Thomson coefficient, and it is denoted by mu sub capital T. In summary, the Joule-Thomson coefficient describes the change of temperature at constant enthalpy as the pressure of gas drops in a throttling process. On the other hand, the isothermal Joule-Thomson coefficient describes the change of enthalpy at constant temperature as the pressure of gas changes. The isothermal Joule-Thomson coefficient is closely related to Joule-Thomson coefficient by the equation mu T equals negative mu Cp. Both coefficients are significant in thermodynamics and are used to understand the behavior of gases under various conditions. Joule-Thomson coefficient mu is defined as the first partial derivative of T with respect to P at constant H. The coefficient can be positive. What circumstance would make the coefficient positive? Think about the throttling process. I mean, when a gas of high pressure is forced to escape through a small opening like a valve, it would experience a pressure drop as it expands. If the temperature of the gas also decreases as a result of the pressure drop, this would make the coefficient positive, and it is called cooling effect. On the other hand, the coefficient can be negative. Let me ask you a similar question. What circumstance would make the coefficient negative? The pressure of the gas drops as it expands through a small opening like the previous case, but the temperature would increase. This causes the Joule-Thomson coefficient negative, and it is called heating effect. The sign of the coefficient of real gases depends on the identity of the gas, the pressure, the relative magnitude of the attractive and repulsive intermolecular forces, and the temperature. This plot illustrates how the sign of the Joule-Thomson coefficient of real gases depends on pressure and temperature. Focus on nitrogen gas. The gray area inside the boundary is where the coefficient is positive, and consequently, cooling effect is expected. Previously, I mentioned about deflating a tire on a hot summer day. When you touch the tire valve, you would feel cool from it. The air consists of 78% nitrogen gas. So, the air may be at the physical state marked by this blue dot that is positioned in the area of cooling effect. And that explains why the tire valve is getting cool during the deflation process. On the contrary, the pink area outside the boundary is where the coefficient becomes negative, and heating effect is expected. Temperature will increase. Gases show a heating effect at one temperature and show a cooling effect when the temperature is below their upper inversion temperature. A gas typically has two inversion temperatures, upper inversion temperature and lower inversion temperature.